Hello and welcome to the History of Chemistry in 15 minutes. This is based on a little book I've been working on called The Mastery of Matter, masteryofmatter.com. You can check out a sample of it. I like to start the history of chemistry in a long time ago with the ancient Hittites. They were the people who first separated iron from its ore. They lived about 1500 BC in the area of modern-day Turkey and Israel. And this is a stone relief from the Hittites at a museum in Ankara. You can see they carve stone, of course, and carving stone is not chemistry. It's just it's physically manipulating matter, changing its shape and so forth. In chemistry, though, we're talking about chemically manipulating matter, changing its properties. And the Hittites were able to extract iron from its ore. This was not the first extraction of a metal from its ore. The Iron Age is after the Bronze Age, actually, so people were already extracting copper and tin from its ore, but iron still used widely today. Amazing development in technology. Let me just show you some little videos here of making iron. This is a video of the finding of bog iron, which is particularly interesting to me as a soil scientist. These iron deposits that form naturally in wetlands, and around here, in eastern Connecticut, there's a state park called Old Furnace, which is the site of some old-time bog iron mining and smelting. So this is just a little video showing a couple of guys that are looking for some bog iron.
And because they've been utilising it year in, year out, they're always looking for new sources. So they'll be out there all the time looking for it and probing for it. And it's something that's,
They're poking in the peat bog here with a stick, a metal rod, and here they find a big chunk of iron hydroxide. So you take a bunch of those, you grind them up, and of course there's other forms of iron ore as well. I'm not sure exactly what the Hittites had, but then you put it in a furnace like this, and this is kind of a reenactment here of an ancient iron smelting furnace. There's your iron ore mixed with charcoal. All right. Now you heat it up very hot in the furnace. They're adding a bunch of air to get it really hot here. Okay, they're getting it over 1,000 degrees. And after a long time of cooking together with the charcoal, what happens is the oxygen is released from the iron oxide or hydroxide, and the oxygen is bound to the carbon as carbon monoxide or carbon dioxide. And what you get is a lump of metallic iron. Now here he's about to remove what's called the bloom, which is kind of a spongy mass of iron from this here. So he's digging in there, he's going to get out some of the slag, which is impurities. And there's the bloom there, a little round spongy or soft mass of iron. And you can pound on it then, and here's some guys in a different video. They heated up a piece of bloom here, and they're going to start pounding it with hammers. Just make it into a sword or a plowshare, I guess, if you want. So you can start banging into whatever shape. You can imagine the impact that a material like that had on society. So that's chemistry, immensely practical, manipulating matter for our own use. And of course, iron was not the first use of chemistry. I consider glass making to be a form of chemistry. This is ancient Egyptian glass from. They were making glass as early as 1370 BC. And of course, people have been using salt for even long before that to preserve food, and they still use it today. This now with refrigeration, it's not as common, but salt modifies the chemical environment of food so that it doesn't decay as quickly. It wasn't until the ancient Greeks, though, that people started really thinking about what matter was and how it worked. This is Democritus, the laughing philosopher, around 450 BC. He and his teacher were expounding this theory that matter was made of atoms. In fact, they were true materialists. They believed that the only thing that existed in the universe was atoms and void. Very modern view, very mechanistic about these atoms bouncing into each other and and combining and so forth, and a sheet drying in the air, and the atoms of water leaving the sheet into the air. That was Democritus. When Plato and Aristotle had some different views. This is a picture from a famous painting called The School of Athens. Plato here is pointing up, and he is pointing to the universal principles. He believed the only thing real was this world of ideal forms. The rest of the world was not really real. Aristotle was a little more, you might say, down to earth, and here he is pointing down. He believed that matter did exist, and that these ideal forms and principles or properties were imposed on matter. And depending on what property you imposed on matter, you actually got a different element. So for example, if you impose the properties of wet and hot on matter, you get air. Hot and dry imposed on matter get fire. And dry and cold make earth, and cold and wet make water. One of the consequences of this is that you can transform things. You can transform one element into another, one substance into another. And so there's this kind of mutability, inherent mutability, or transmutation that is possible. This is an ancient alchemical manuscript. Alchemy comes from an Arab word, alchemia. And so it's like the chemistry, you might say. This is from a manuscript of Zosimas, an old alchemist, and they were able to do back, 300s, 400s AD, they were doing things like plating copper rings in silver. And at first it seems like they knew they weren't really changing it, they were just adding something to it. But this kind of changed when the alchemy melded together with Aristotelian theory. And so the alchemists started to believe that they could actually change one metal into another. And the Arabs brought this to Europe. And so you've got this kind of picture of the alchemist. This is a famous painting by Joseph Wright. This picture of alchemists always trying to turn the base metals into gold. And they were looking for something called the philosopher's stone. The philosopher's stone was that substance that would be able to do that, to transform the base metals into gold. Of course, some of these alchemists were nothing more than frauds, and you see this in the Canterbury Tales, actually. In Chaucer's Canterbury Tales, he tells the story of an alchemist who basically takes this guy for a ride and takes all his money by telling him he's going to teach him how to change mercury into silver, and of course he just fakes it and just takes the guy's money. Chaucer writes, "Come forth, if it's a fool you'd like to be, and learn about the art of alchemy. If you have money, then step forward, sir, and you too can become philosopher." But it wasn't always fraud. The great physician and alchemist Paracelsus, he used chemistry to heal people. He used antimony as a laxative, and mercury to treat syphilis, and other chemicals in his practice. So it was practical as well. When we start to see this shift from alchemy is with Robert Boyle, who was sympathetic to alchemy, but he was clearly breaking from its kind of mystical and kind of nebulous nature. He came up with the first seemingly modern definition of elements, that they are simple substances that can't be broken down into simpler substances. And he was an atomist, by the way. He believed in atoms. So atoms the atomic theory was not gone until Dalton. It showed up at different times through history. And this is Robert Boyle. So in addition to his gas laws, he also developed the first kind of modern view of an element as a simple substance that can't be broken down into simpler ones. But alchemy kind of hung on in the form of the theory of phlogiston. G.E. Stahl in the early 1700s came up with the phlogiston theory of combustion. Now, according to this theory, when you burn something, what happens is it releases this element called phlogiston, which is kind of a black, greasy element. And you can picture that black stuff that forms on like a pot over a campfire. This is the reason I say this is kind of like alchemy, is because it kind of harkens back to the element of fire, all right, and that same sort of thing. Interesting. There are substances called calx, and things like iron oxide would be considered a calx. Now, charcoal is almost pure phlogiston, so if you put phlogiston and iron oxide together and heat it up, what happens is the phlogiston goes back into the calx and makes the metallic iron. That's how the phlogiston theory would have explained the smelting process. So it was actually a powerful theory in terms of explanation. But one of the problems it had is that when you burn metals with charcoal, or when you burn metals, even though supposedly they lose phlogiston if you burn a pure metal, it supposedly loses phlogiston, and yet it gains mass. Now, they had all kinds of sort of ad hoc theories, but the first guy who really kind of brought that problem to light and dealt with it was Antoine Lavoisier. He was a tax collector in France. He actually lost his head in the French Revolution after coming up with all his great theories. But he came up with what's called the oxygen theory of combustion, actually discovering oxygen, according to some historians. And he came up with this idea that no, there was this element in the air called oxygen. So air was actually a mixture of different elements. And when you burn something like a metal, what happened was the metal was combining with that oxygen to make a compound, a gaseous compound in the case of carbon. And in the case of a metal, the reason the metal got hot, it got heavier when you heated it, was because it was combining with another element. And I think Lavoisier is called the father of modern chemistry, and I think it's because really with Lavoisier we first have this picture of chemicals, elements combining and breaking apart from each other and recombining to form different compounds in a quantitative way. Lavoisier made heavy use of the analytical balance. He wasn't the first one to use a balance, but he did make heavy use of it, and the conservation of matter, the principle of the conservation of matter, that matter is neither created nor destroyed in a chemical reaction, that it's just changed from one form into another, and actually it's just atoms of different elements combining and making different combinations. This is just a picture of Lavoisier's analytical balance, very sensitive balance that he used. There were people who resisted this, but Lavoisier really, by the time he was done with his theory, we basically had this modern picture, this modern scheme of matter, classification of matter. Matter can be divided into mixtures and pure substances. Mixtures can be separated physically. And then pure substances can be either compounds or elements, and compounds can only be separated chemically. All right, and we can get into a little more detail here, and we will. But for now, this is modern chemistry, is when we have this kind of paradigm of matter. Not everybody switched from the phlogiston theory so easily. Joseph Priestley was a brilliant scientist. He actually invented the carbonated beverage, discovering CO2, figuring out how to put it into water and make carbonated water, and that's among many things that he did. Actually, some of his experiments were borrowed by Lavoisier and reinterpreted, and that's how Lavoisier discovered some of his stuff. So Priestley was brilliant, but he held on to the phlogiston theory. He would not change his view of combustion, and so he kind of got stuck in the past. But again, he made some great contributions. The carbonation of water was one of my favorites. I just love seltzer water. I got this new soda stream that I use all the time to make myself seltzer water. But the revolution created by Lavoisier is one of the examples that Thomas Kuhn uses in his book, The Structure of Scientific Revolutions, as a major paradigm shift. What happens is in normal science, nobody really questions the underlying theories, the so-called laws, for a while. And what happens is anomalies start to crop up, and they start to persist. In this case, it was some anomalies related to phlogiston theory about the gaining of mass by metals and so forth. And then some young scientist, usually a young scientist or someone from outside the field, they start to pick up on this and question this, and they challenge it. And they don't have these kind of deep-set notions that are stuck in their minds. They haven't been working their whole lives on this theory, so they don't have this kind of vested interest. They're willing to question it, to challenge it. And that's what Lavoisier did. And then what happens is, when they come up with a better theory, a better worldview, a better picture of the world that actually works better and fits the data better, then the paradigm shifts. Is this a duck or a rabbit? Kind of depends on your perspective, and in this case you can look at it and you can kind of switch in your mind back and forth between the two. But in a true paradigm shift, once you switch, once your worldview changes, you look at the world differently and you can't see it the same way again. And that's what happened in Lavoisier's time. and we'll move on and further in chemistry in our next issue.